Welcome to the training module on ADR34 series micropower high accuracy voltage references. This training module will introduce ADR34 series high accuracy voltage references, their key features and application circuits. Although they are not new technologies, voltage references have a major impact on the performance and accuracy of analog systems. They are used as a precise analog meter stick against which the incoming analog signal is compared or the outgoing analog signal is generated. The standard reference ICs are often available in series or three-terminal form, that is, V-in, common and V-out. The series types have the potential advantages of lower and more stable quiescent current, standard pre-trimmed output voltages and relatively high output current without accuracy loss. However, shunt or two-terminal references like diode references have more flexibility regarding operating polarity but more restrictive as to loading. Here we discuss some key performance parameters. Tolerance indicates the accuracy of the reference. It is a percentage of the nominal value, which is not even a unit. Temperature drift or drift due to aging may be to an even greater problem than absolute accuracy. The initial error can always be trimmed, but compensating for drift is difficult. Noise in voltage references is often overlooked, but it can be very important in system design. Load sensitivity or output impedance is usually specified in microvolt per milliamp or load current or milliohms or parts per million or milliamp. It is a measure of the change in output voltage due to a change in input. Noise is an instantaneous change in the reference voltage. It is generally specified on datasheets, but system designers frequently ignore the specification and assume that voltage references do not contribute to system noise. The ADR34 series of voltage references are low-cost, low-power, high-precision CMOS voltage references, featuring plus or minus 0.1% initial accuracy, low operating current, and low output noise in a small SOT23 package. For high accuracy, output voltage and temperature coefficients are trimmed digitally during final assembly using analog devices patented DigiTrim technology. Stability and system reliability are further improved by the low output voltage hysteresis of the device and low long-term output voltage drift. Furthermore, the low operating current of the device, which is 100 microamp maximum, facilitates usage in low power devices, and its low output noise helps maintain signal integrity in critical signal processing systems. These CMOS are available in a wide range of output voltages, all of which are specified over the industrial temperature range of -40 degrees C to 125 degrees C. Like all bandgap references, the ADR34 series references combine two voltages of opposite temperature coefficients to create an output voltage that is nearly independent of the ambient temperature. However, unlike traditional bandgap voltage references, the temperature-independent voltage of the references are arranged to be the base emitter voltage, VBE, of a bipolar transistor at room temperature, rather than the VBE extrapolated to 0 degrees Kelvin. The VBE of a bipolar transistor at 0 degrees Kelvin is approximately VGO, the bandgap voltage of silicon. A corresponding positive TC voltage is then added to the VBE voltage to compensate for its negative temperature coefficient, or TC. The bandgap voltage, VBG, is then buffered and amplified to produce stable output voltages. The temperature coefficient relates the change in output voltage to the change in ambient temperature of the device, as normalized by the output voltage at room temperature or 25 degrees C. The ADR34 series patented DigiTrim technology to achieve low temperature coefficient. Normally, the reference circuit maintains an internal voltage source that has a positive temperature coefficient and another internal voltage source that has a negative temperature coefficient. By summing the two together, the temperature dependence can be cancelled. In the ADR34 series, the temperature-independent voltage of the references are arranged to be the base emitter voltages at the room temperature, and a corresponding temperature coefficient voltage is then added to the VBE voltage to compensate for its negative TC. One of the key parameters of the ADR34 series is long-term stability. Regardless of output voltage, internal testing during development showed a typical drift of approximately 30 parts per million after 1,000 hours of continuous, non-loaded operation in a 50 degrees environment. It is important to understand that long-term stability is not guaranteed by design, and that the output from the device may shift beyond the typical 30 parts per million specification at any time, especially during the first 200 hours of operation. The systems that require high stable output voltages over long periods of time, the designer should consider burning the device prior to use to minimize the amount of output drift exhibited by the reference over time. Load regulation refers to the change in output voltage in response to a given change in load current, and is expressed in microvolt per milliamps, parts per million per milliamps, or ohms of DC output resistance. This parameter is important if the reference load current changes while the reference is operating. The parameter is a DC parameter and is specified typically at DC. It accounts for the effects of self-heating. In general, load regulation deteriorates inversely with the rate at which the load current changes. Output capacitors are recommended to stabilize the output voltage in applications subject to low current transients. The circuit shown in the figure illustrates the basic configuration for the ADR34 series. A 1 microfarad capacitor and 10 microfarad electrolytic or ceramic capacitors can be connected to the input to improve transient response in applications where the supply voltage may fluctuate. An additional 0.1 microfarad ceramic capacitor should be connected in parallel to reduce high frequency supply noise. A ceramic capacitor of at least 0.1 microfarad must be connected to the output to improve stability and help filter out any high frequency noise. Here we list all the product offerings under the ADR34 series family. This series of references are available in 7 fixed output voltage options from 1.2 volts to 5 volts, featuring 0.1% max initial error and 8 parts per million per degree C max drift, able to source 10 mA and sink 3 mA. They specify 250 mV max dropout voltage with a 2 mA load, operating from a 2.3 volts to 5.5 volt supply. The ADR34 series draw only 85 microamp max when enabled and just 5 microamp max in shutdown mode. This diagram shows how to connect the ADR3450 and a standard CMOS op-amp, such as the AD34xx to provide a negative reference voltage. This configuration provides two main advantages. First, it only requires 2 devices and therefore does not require excessive board space. Second, and more importantly, it does not require any external resistances, meaning that the performance of this circuit does not rely on choosing expensive parts with low temperature coefficients to improve accuracy. In this configuration, the Vout pins of the reference sit at virtual ground, and the negative reference voltage and low currents are taken directly from the output of the operational amplifier. This figure shows a bipolar reference configuration. By connecting the output of the ADR3450 to the inverting terminal of an operational amplifier, it is possible to obtain both positive and negative reference voltages. R1 and R2 must be matched as closely as possible to ensure minimal difference between negative and positive outputs. Resistors with low temperature coefficients must also be used if the circuit is used in environments with large temperature swings. Otherwise, a voltage difference develops between the two outputs as the ambient temperature changes. The figure shows a configuration for obtaining higher current drive capability from the ADR34 series references without sacrificing accuracy. The op-amp regulates the current flow through the MOSFET until Vout equals the output voltage of the reference. Current is then drawn directly from the Vin instead of the reference itself, allowing increased current drive capability.